Our first speaker this afternoon is Margarida Telo da Gama, and the title of her talk is Little Crystals, How Do They Wet?
Well, thank you very much. Thank you, Epifanio. Thank you for the organizers of this program for having me here. And what I thought I would tell you about is some recent work we've been doing on substrates, structured substrates, when we put a nematic on it. And this is related to, but a little bit different from the work you've been hearing about from Nigel, Mottram, and other people working on cells. We're actually interested in how the nematic orders, and in fact how defects may emerge, but we're also interested in the free surface. So we're looking at this problem, which is slightly more academic, but there are some similarities with some of the things that you've been listening to. And I thought I would give you a fairly general introduction of what I mean by wetting and so on. But I'll try to go quickly, otherwise I won't get to the part which is sort of new. So the first thing is that I'm going to talk about wet and dry states in the sense that I mean equilibrium thermodynamic states. And you probably heard and even studied problems where you see a fluid, a liquid generally, that wets a surface. And what I want to point out, because it will be important later on, is that there is a third player. I'm talking about equilibrium states, and the interface between the liquid is a proper interface, so there is a saturated vapor that is always present as well. So there are basically three bulk phases, and I'm going to look at the properties of surface states when we change some dynamic parameters or you change the substances. This is a very simple outline, and I'll give you a few words on a long story, which is wetting of simple fluids at flat substrates, and then I'll try and say a few words about nematics. This is really old work, and then I'll try to come to the problem which is more has been revived in recent years, which is what happens if the structure or if your substrate has geometrical structure on micron scales. So mesoscale, not atomic and not fully macroscopic, but large enough that you can think of things in a way which you'll see will lead to probably new surface states. Okay, then I'll show you some results on nematics at structured surfaces that we've been doing, and in fact this is work that has been going on for 4 or 5 years, and in fact I wasn't even involved in the beginning. I was involved only very laterally. And then I'll try to end with some outlook and open questions, okay? So one of the main players, or the main quantity is going to be the surface tension, and you all know what the surface tension is, but in this context, rather than a force along the line that tries to stretch the interface, or contract rather, sorry, I'd like to think of it, and it's more useful for what follows, as an energy, a free energy, the work that you need to do to increase the area of the surface under isothermal conditions, so at constant temperature. And another key quantity, when you have these three phases, I told you there are three phases in equilibrium. One is represented there by the solid, and then the other one is the liquid, which is a droplet. This other one is the gas that you don't see. But basically, under mechanical, at least mechanical and thermodynamic equilibrium, there is a relation between these three tensions, and through this relation you can define a contact angle. And this contact angle is old, you know, this is Young's equation, and this actually refers to equilibrium conditions, and I'm just getting to the definitions that I really intended to. So everybody, I mean, this is 1800s and something when that equation was written down, but there was a sort of revolution in the 70s when John Kahn, at least it's attributed to John Kahn realized that if you start from a situation where the wetting is partial, so this droplet does not spread over the solid, then if you increase the temperature as you approach the critical point of the coexisting liquid and vapor, then there should be a transition to completely wet. Or it could be completely dry depending on the value you start off. If the droplet is in fact with a contact angle which is pi/2, so it could go either way. But if the contact angle is greater than a certain value, you go to one state, one surface state, otherwise you go to the other one. And in simple fluids, these things are completely equivalent, although wetting is much more common than drying, although drying is also important in some applications. Okay, so I'll just give you the dates. The dates are a paper by John Kahn in 1977. At the same time, there is another, so this is based, I'm going to go a bit through that, because the liquid crystal application actually uses basically the same ideas. But there was a microscopic approach using density functional theory that you've been hearing about exactly the same year. So that 977 is really 1977 by Ebner and Sam, that actually predicted essentially, if not wetting, pre-wetting, which is sort of closely related. But 1 year before, and I think this is interesting, in fact, pneumatic pre-wetting had been obtained and in fact published by Sheng in the context of liquid crystals. So for the liquid crystals, I think the way to think about it, the solid is the substrate, the droplet is the pneumatic, because we actually want to look at differences between a normal fluid and an ordered fluid, and then the vapor, if you're under coexistence with the isotropic liquid phase, would be the isotropic liquid. Okay, so you have three phases, and you may have or not this transition. Of course, a liquid crystal is different from a normal liquid. You don't have a critical point, so this first argument by Kahn doesn't really or cannot be used directly in liquid crystals, and there should be other differences, and this is really what people have looked at. In brackets, I have actually the number of citations of these papers. I had to look at the references in the web, and now they give you that information. And you know, even although I was a bit surprised, I didn't think the liquid crystal paper had received so much sort of interest compared to, but you know, it compares pretty well with the fancy density functional theory of Ebner and Sam, which was really the state-of-the-art microscopic theory at the time for inhomogeneous fluids. But of course, I think at least the argument, which is not 100% rigorous, that Kahn gave, which sort of made this as a universal transition, really distinguishes these contributions, I think, and that didn't surprise me, that Kahn's paper really had much more citations than the other two. Okay, so this is macroscopic, this is thermodynamics, and I want to look at the microscopic aspects of these. And so on the macroscopic level, at wetting, at this transition, this contact angle vanishes, okay? The droplet spreads, but at the microscopic level, at the same transition, you can think of this as two interfaces, three phases and two interfaces. And there is the distance between the two interfaces, solid, liquid, liquid vapor, the distance between the two interfaces increases to macroscopic values. And this is one of the things that is important in analyzing these systems theoretically and might be important in applications. Okay, so this is another paper, rather famous. I'm not quite sure I have a number of citations. This is a few years later by Nakanishi and Fisher. I think I don't like these when these things come in little bits because, okay. Well, the wetting problem was put in the context, the general context of surface phase transitions. And this was a very important piece of work. This is all mean field, and this is really the type of free energy we've been looking at. It's not the Landau-Duchenne, but it's the Landau free energy. And what do we have? We have, I call it Fs, and there is a gradient squared term. M is the magnetization. This is in the context of magnetism, but it's really a scalar order parameter. This would be the Q, and I'm going to talk about it later. And then there is a bulk term, which here I call omega M. I didn't actually call it. I just got this from a recent review, the most recent I found, the 2009 Review of Modern Physics by Daniel Bonn and co-workers. Okay, so there is a bulk term. This would be the polynomial in Q for the liquid crystal problem, or a polynomial in M for the magnetic system. And then there is the plastic term in the liquid crystal literature, and the cost of actually having a gradient, a density gradient, or an interface. And then there is this little guy here, and this little guy there is the surface potential. So the difference between some of the free energies we've been looking at here until now is that now explicitly I'm going to integrate this bulk term plus the gradient term over half the space, and I have to add a surface term which tries to describe how the surface interacts with the liquid molecules. Okay, so this is at the level of the Landau theory. I really shouldn't be talking about molecules, so this is the coupling between the surface and the field that describes the liquid state. And in the Nakanishi-Fisher and in magnetic systems, what you do for this term is what you do for the bulk terms. You expand in terms of the value of the magnetization at the surface. So this is one field, two fields. You have two surface fields, and you have one term which is linear, one term which is quadratic. The linear term is how the surface likes one phase better than the other. So if it attracts or repels the molecules with comparison to the bulk. And then the second term is really just surface enhancement, which for normal liquids is actually always negative. It's just tells you that because there is a wall, there are no liquid molecules on the other side, and therefore there is a term which is negative. Okay, I spent a little time with these, and I've already mentioned quite a bit of well, the similarities with the nematic problem, and so I think I can go quickly through that. Again, this, as I said, I tried to say here, even in 77, I mean, the paper by Sheng predates the Kahn paper by 1 year, so there have been applications to liquid crystals and to liquid crystal wetting. Tim called it orientational wetting, and he has a review on it, which came out in 86. But many people have been applying these, but more than that, people have been trying to see experimentally what happened. So I thought I would give you in a few slides. If I'm boring you, tell me, and I'll go quicker. But just in a few slides, some of the major similarities and differences with the liquid simple fluid scalar order parameter problem that I referred to. So I don't have to go on about what the nematic is. It's the simplest ordered phase, and for the purposes of this talk, I'm only interested in the simplest of them. In Lisbon, we're beginning to think about cholesteric wetting, and it's a lot more complicated. But this is just a nematic, so this is the simplest. I think this is a picture from Oleg. I'm not even sure. I got it from the internet some time ago. And so this is a nematic, and you can describe at the level of the bulk phase, the bulk nematic phase, you can describe the elasticity of this nematic using the celebrated Frank elastic free energy. And I call it macroscopic approach because this is really the approach you should use at the level of thermodynamics, at the level of stable nematic phases, okay? Because it really, these are the distortions of a ground state which has already order. And so I'm not going through it. You've seen it many times. There are 3 of them, and then there might be some surface ones, but I'm not getting into it. That's one of my open questions in the end. So here is Charles Frank. I think you've seen the free energy, and I'm pretty sure you've seen the pictures of Frank, but just a tribute to Charles Frank. He was head of department in Bristol when I went there as an undergraduate student, and I didn't come to appreciate his work until much, much, much later, although he was always asking very intelligent questions at the seminars when I was a graduate student. So this is the free energy of distorting bulk nematic. And so you have different types of distortions. And this energy is nice because it's quadratic. You can do other things with it. And for example, in some limits, if there is no anisotropy in the elastic constants, you can actually write down something that looks very much in 2 dimensions, like an equation that you love and you've solved, and this is very useful if you want to analyze some types of defects. Okay? In equilibrium phases, the effects are not really stable. If you let these phases forever, they will annihilate, and so the bulk is kind of, it's a ground state which is ordered. It doesn't have these types of defects. But what I'm going to try and show you in the end is that for some of these structured surfaces, you cannot avoid the defects. So it's nice to know how they contribute to the free energy and how you can, in some cases, write down analytic expressions. So this is one of the famous ones. I don't know, didn't actually go and look at the paper of Frank, but if you solve the equation that I had before, you find that you can write the free energy contribution, and there is this logarithmic contribution, I'm sorry, where big R is dimension of the system, or typical dimension of the system, and that's some core where you have to sort of stop your integration, otherwise the free energy blows up, and then there is some free energy associated with the core, okay? So I call this mesoscopic free energy, and this is the lowest level of free energy that I have to work with if I want to look at the interface, or surfaces and interfaces at the same time. The interface, you can think of it as a huge defect, you know, what the nematic actually melts at the interface between the isotropic and the nematic phase. And this is a lovely theory, not only, I mean, I never met Landau, but I wish I had. And the other one, well, maybe I will, never mind. I know I'm being filmed, but this is De Gennes, which I've met when I was still very young and in America. And I have lots of stories, but not to broadcast to the world about De Gennes. Anyway, so this is the Landau-De Gennes theory. You've seen it. No. I'm being, my students are probably watching me in my postdoc. So anyway, so I got a bit lost. That's what men do to me. But okay, so you've seen the free energy many times before. This is the full-blown second order theory. I want to insist on the second order. You know, I learned how to do Taylor expansions in Britain. And they always told me that, you know, I should be consistent. If I stop in second order, it's second order, and it's not one third order term if I need it or when I need it. And so this is a second order theory, and these are some typical values for 5CB of the coefficients A, B, and C in the bulk free energy. I'm not going to show you the double well. You've seen it so many times throughout this workshop, and I want to concentrate a little bit. Oops. I might as well put it all. So I rescale variables. It's much nicer if you're doing theory to rescale variables. And so I take variables such that my order parameter is 1 in the nematic and is 0 in the isotropic. And I also rescale my space in terms of the bulk correlation length, which again, if I'm near the nematic isotropic transition, this is really, it can be large. Because the transition is weakly first order, but it can be very large. And so I'm looking at systems where there is structure surfaces later on that varies between 10 and 100 correlation lengths. I don't like to go below 10 because Landau should not work if you really well below the correlation, well, not below. You have to be bigger than C. This is the correlation length in terms of the variables or parameters that I introduced in my Landau theory, Landau-De Gennes. And I also, this is important in some cases, the elastic anisotropy of the liquid crystal is positive. This means that if I have a free surface, the Landau-De Gennes theory, doesn't mean the real liquid crystal, the Landau-De Gennes theory tells you that the molecules lie flat on the interface. So you have homogeneous planar anchoring at a free surface. In these units, the nematic isotropic transition occurs at t equals 1, and so this is also convenient. And anchoring is the strength of my surface potential, but where these transitions occur, these surface potentials, through some dynamic arguments, but also through some detailed calculations, you can show that this transition anchoring is of the order of the free interfacial tension. Okay, so if I tried to look at some data, even asked Tim for 5CB for the surface tension of the nematic isotropic interface, and I had to estimate it. I actually estimated from a paper that Tim is a co-author. He has the free nematic vapor or the free nematic surface that has a jump, you know, discontinuity at nematic isotropic transition. And I've learned when I looked at these things many years ago that, okay, that's the liquid vapor interface, and if I think about densities and so on, the nematic isotropic interfacial tension should be about 100 times smaller. So it has 39 per centimeter, and I divide it by 100, and I get these, whatever it is, types of values for the surface tension of the nematic isotropic interface of 5CB. Although any better numbers in this I know is exaggerated, but I was looking at correlation lengths of 5CB near the transition, and I get this from a paper. I'm not going to tell you which one, but I think this is really overestimated. But anyway, these correlation lengths should be nanometers or above. I'm close to the nematic isotropic transition, so this transition is weakly first order. This length does not diverge, but it's large. It's larger than the molecular distances, typical distances, and it can be much larger. How much larger, I don't know. It depends on the temperature. This is exactly at the transition. So just to give you some numbers that may or may not be relevant. So, okay, just the surface field. It's the only last bit that I need to talk about in a little detail, and this is the simplest linear coupling, that if I think of the magnetic system, this is sort of ignoring the term, the surface enhancement term, which if you're just talking about order, this is probably okay. We've done some calculations for the quadratic potential. So this typically has a strength, W, or omega in this funny, and then you have the favored tensor. But if you think about it, you don't actually have two free parameters, you only have one free parameter, because if that tensor gives you homeotropic anchoring, and if the interface, the surface, this surface that is the boundary, is not biaxial by itself, then this preferred anchoring should be uniaxial, so really the S that comes from there can be absorbed in W, and you actually only have one free coupling strength. If you have two terms, then it's slightly different. You have two surface fields like you had in the magnetic problem. And so, depending on the type of coupling, you have different coupling terms and fields. Okay, the challenge. I think I already said that because we have surfaces and interfaces, not only the order parameter itself varies, and it varies on the order of Xi, because the surfaces in, well, at least the free interface, that's the scale over which Q varies. But then, if we want to look at some more details, the surface patterns, if they're on the micron, submicron scale, they'll introduce changes on that scale. And if you really want to look at wetting layers, eventually you have to go much bigger. So you have to go to a length scale, which is essentially macroscopic. In a calculation, it never is macroscopic. It has to be bigger than the others. And so you have many scales and many competing states. So if you want to make some progress, first of all, you need to understand what you're looking for so that you don't look at the wrong solution. And you have to rely and make some tests. I mean, thermodynamics is wonderful because, if you get it wrong, you very easily violate thermodynamics. And so never forget thermodynamics. Okay, so in addition to many length scales, we have many structures, or we may have many structures, and we have differences in free energy that we have to estimate with an accuracy or precision which is better than the difference in energy of these competing phases. That's basically why numerically this is a bit of a challenge, and I think this is really why this is being done now and was not done 30 years ago when we all looked at the flat surfaces. Well, at least some of us did look at the flat surfaces. It's because computers are much more powerful, you have better algorithms, and I may say one word or two about that, but not too many. I shouldn't forget that, this is a slightly relevant point, is that now it's very easy to make structures on the micron scale very controlled. Again, I don't think this was possible 30 years ago. So for simpler fluids, this is really one of the motivations. There are others that I'll leave to the end. Okay, so I already told you that with this theory, the nematic isotropic interface has some value, and it actually prefers, this is the case, the molecules lie flat. This is, you can do the wetting problem in this context, so you can put a surface. This surface can attract or enhance the order with some anchoring strength, W, and if you plot a dry state versus a wet state, the wet state is the one where the nematic layer is thick, the dry state is the one where there is no order, there's an ordinary isotropic liquid, and these are the profiles that you can find. Typically, these are two branches, they cross at a point, so these surface states do coexist, and there is a wetting transition at a value. We can use the balance equation to get the orders of magnitude. but Tim and other people, Tim actually did this. This was the last paper that I know of for the very simple model within Landau theory that did these for antagonistic conditions at the surface and at the far end, in the isotropic phase. But there are other related works. In those days, I worked with full microscopic series and looked at the effects of density, which can be important, but I'm forgetting now because when you structure the surface, you already have enough problems without the density. So there's a lot of words there, but you don't need to look at them because I've already told you. If the surface and the interface, for example, are homeotropic, your system really costs energy to distort. So your system will be uniform, and you can actually write down a very nice analogy. Mathematically, you can find a mapping between these and surface free energy that I told you is used in simple fluids with scalar order parameters. You can recover all the limits, all the previous results if you want to do so. And what is interesting is that people have actually looked at these things. The geometries that they usually look at is between two parallel plates, and they start from the isotropic phase, and they see how the amount of order, how the number of layers of ordered fluid, of pneumatic, depend on the temperature this is pneumatic isotropic temperature. Okay, and for example, this is one of the papers. I'm only going to show you one or two. And this is fit, in fact, in the paper. If you look at it, it's fit by a Landau theory, and the authors claim it's in very good agreement with Landau theory. So for most of these liquid crystals, they all wet except 5Cb, which is a little bit funny. 5Cb is the one below here. And I'm only going to show you another experimental result because it was already mentioned here by Doug Cleaver. This is the most recent that I know of that looked not only at the whole series of NCBs, but also looked at many different surface fields. So they prepared this surface with very different CF3 monolayers and other types of monolayers. And so again, this is already okay, isotropic pneumatic transition. And so what you see, it's the same geometry, two plates and two surfaces, and fairly large at a macroscopic distance. And you come from the high temperature phase, and you see how the order is changing as you change the temperature. This is ellipsometry. The other one was evanescent wave, but I'm not an experimentalist. I only know enough to know that there are different techniques. This paper is quite interesting. It's sort of local almost, but because they did try two things which are sort of relevant. One I'm not going to. They actually measured how the pneumatic order grows with the temperature, and they found a log. This is the celebrated short-range results, which in simple fluids you don't see because there are always dispersion forces. And well, we can maybe not discuss why they find that. The other thing which I think was very brave of them was that they actually tried to plot a full global phase diagram, which reminds you of the one I showed you for the magnetic systems. They're really very, very honest. They don't try to fit these to Landau theory. They just say that there is something they don't understand, and I think I was looking in the literature, which is these things seem to wet the substrate when it's homeotropic. But if it is planar, they don't. So wetting seems to be coupled to an anchoring transition. And how do you go about it? I'll just mention another. So this is what I was planar. There is a problem with planar anchoring, and there is well, something that Tim also looked about and was observed experimentally, at least. Tim can maybe say a bit more about it, is that if you have planar anchoring, I mean, you might think that if it is random planar, nothing will happen. But the surface, you can have this transition at the surface by itself. It's random planar, but then eventually above the pneumatic isotropic transition, this layer may acquire a two-dimensional surface pneumatic order. And these people actually claim they've seen that. Tim actually looked at the transition. This transition is kind of rather special, but I'm not going to mention any. So I think, in all, I think pneumatics flat surfaces, of course, they're different, and there are things we don't understand, and that Landau series does not describe in detail, which is not very surprising, because after all, it's the simplest theory you can use to describe these types of systems. But all in all, the picture, the overall picture, seems to be captured by this simple version of Landau theory, that you get wetting, that you get surface order, enhanced surface order that can, by itself, this would not happen in a scalar order parameter field. So I think this is, we understand 80% maybe. Now structured surfaces. I put it up this slide, but this is really, this is not what I'm going to talk about. I was looking at some pictures in the internet, and I saw this pretty picture, and then the legend that came with it, that it's, you know, I mean, a droplet on a structured surface is influenced by a great deal of parameters, including surface, blah, 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 blah. Well, that's exactly what I don't want to do. I don't want to look at all the quantities that affect this problem. I want to look at something simpler, much simpler, and restrict the attention to something that has been, has a long story, but has been rediscovered more recently, about 10 years ago. And this is that, if you now have, this is the substrate. Substrate is the pinkish background. And now if you have a substrate, you don't see the vapor or the saturated phase, or in the nematic language, the isotropic phase. You only see that this substrate will absorb or will orient a little bit of fluid. And then this is the wetting picture I was talking about before. But if these things, if these pillars or if these ridges are big enough, something else can happen in between. So there can be a filling transition. And you can define filling using thermodynamics, like you defined wetting. And this is basically what I want to look at. And so this is thermodynamics. Again, as I said, it's nice to have some anchors that you have to, if you now have this substrate that undulates, has some kind of structure. So of course the surface area is bigger than the projected area, and I'm going to call that R. There's an old equation by Wenzel that says basically that if you have this substrate, a surface that likes to be partially wet, so the droplet spreads but not completely, it enhances, so the amount of order, the amount excess surface will enhance this effect. By contrast, if the surface is like Teflon and it doesn't like the fluid, then by roughening it, it enhances the drying effect. So there is an extra bit that comes just from the extra surface. And if you define the apparent contact angle, then you can say that this is where the wetting transition will occur if you only take into account the excess area. Filling is a little bit more subtle, and it's a little bit more complicated. I'm not going to go through it in detail. There are quite a few recent papers on the subject. But now, you know, if you describe that, this is a sinusoid. So the g of x is really the profile of the structure. And you can find filling as a transition when you satisfy this equation. There is a derivative of the profile. And basically, this is really, it's the same. It's just trying to calculate the excess area. And so you can calculate, and you can find that in general, to be a surface phase, then there are certain conditions on the derivatives. It has to be a local minimum, basically. And this is thermodynamics. And what you find is that this occurs usually before wetting. And that one occurs, the other one, the simple fluids, the other one follows. Okay, so I just want to give you. So I'm only going to look at these rough surfaces or rugged surfaces or periodic. I mean, they're not really rough. I use R just to tell you how much more area, surface area I have, but this is a periodic surfaces, so they're not rough at all. Now I'm going to start with two just very brief mention. How can this be seen? These scales in some experiments. I'm not going to discuss them. Julia will be here next week, Julia Yeomans, but in Oxford, they've been looking not at the free surface, at the cell problem, with viruses. So of course, if you have viruses, all these scales will go up. When I have the bulk correlation lengths for 5CB becomes that for the FD virus, and you can actually increase considerably the size of your system. And this is a problem that this is again recent paper where they have a rugged substrate and they have a pneumatic on top of it. It's a free surface rather than the type of surfaces I've been talking about. This is a free pneumatic surface, and there are certain differences that I'll comment in the end. But in this case, for example, in the first experiment, they claim they can use these geometries to measure the elastic anisotropy. In the second one, the claim is that they can use the defect lines that form spontaneously in these structures to assemble particles, colloidal particles, because they can control the sizes, the distance between the defect lines. But so I'm not very interested in the applications at the moment because I haven't got there. It's not because I'm not really interested, it's just I haven't got there. So let me just recall. If I now look at the wetting equation, when there is this excess surface area, what is there in addition to the simple fluids? And what is there in addition for the liquid crystals is some elastic term. Because now if you have a geometrically structured surface, you cannot avoid distortions. They can be smooth, they can be singular, but they will distort. Only in certain limiting cases you can recover the uniform states. And you can. I mean, of course, the planar limit, you will recover the uniform states. But everywhere else you'll pay some energy because the pneumatic molecules will get a little bit confused like my computer, and they don't know how to follow all the groove geometry and all the surface fields. So this is what is written there. For pneumatics, we have to remember that this elastic term can actually drastically change the picture. I'm going to give you the overview because the details are sort of complicated. And in Lisbon, we've looked at 3 different geometries, not just to do them all, but for simple reasons. I mean, the wedge is a particular case where you can actually make, at least for simple fluids, you can make a connection with the flat wetting problem. There is a hidden symmetry here, and you can look at that. And Andrew Parry has been looking at this for 5 or 6 years. There's just a paper today on Physical Review Letters on these types of substrates for simple fluids. And the belief is that in these cases, this filling transition is related, as I said, through a hidden symmetry to the wetting transition. And but the fluctuation effects are much more important. This is what drives Andrew. And this is actually, to be honest, what made us look at these, because he thought that getting the continuous transition would be easier with liquid crystals, but it's not. And, well, the sinusoidal surface is kind of, it's not singular, and it's kind of nice. And then we looked at this third one, which has an advantage with respect to the other two, which is that you actually can separate the grooves. Okay, so you have an extra surface field. In the first two, the excess area, basically, this is for the triangular, we didn't look exactly what's there. It's really repeated periodically, okay? And so in this square one, we can actually separate the groove. So we can see how much comes from an isolated groove, how much comes from the interaction between the interfaces. So that was the reason to look at these 3. And, well, the overview, and I'm going to give you the overview. Well, I have 5 minutes.
Sure.
5, 10,
15.
15, because I started 5 minutes later. Okay, so I'll go through the 3 cases quickly, but I'll go through the 3 cases. For this triangular grating, you don't have filling transitions, but you don't have them for the simple fluids either. So in a way, this triangular grating.
Excuse me, could you give an idea of the size of the grating?
Yes. I'm going to show you phase diagrams. The size is between 10 and 100 xi.
So 400.
So if I take
40 nanometers.
Yeah, but
How much do you say? How many
well,
times?
I said the xi could be anything.
No, 40. You said 40, but how many times you see?
No, yeah, that's
Because
in
one
terms
of
of
your
xi.
slides, you said 40.
In terms of xi, I varied. I'm going to show you the phase diagrams. Of course, there is a size dependence.
Yeah.
There is a size dependence on the overall pattern.
So this is microns.
For 5CB, I don't think it's microns. I don't know what's the correlation length of 5CB at the pneumatic isotropic.
But if you multiply it by 10, it will be...
Well, you said 40 nanometers times 10.
Yeah, but I think 40 nanometers is exaggerating.
It's a little bit more, right?
Yeah. I don't know. Well, I had a little trouble with the correlation lengths of 5CB. But yeah, it should be, it's submicron. It's not tenths of nanometers. It's not molecular, it cannot be.
Fraction of micron. Micron is 1,000 nanometers. So it's
Fraction of a
fraction.
nanometer.
Oh, say that again?
It cannot be a fraction of a nanometer.
Of course.
So this is
fraction
on
of
the
nanometer is a micron.
colloidal scale for me, to a theoretician. It's colloidal in the sense that it's many molecular diameters. Many could be more than 10, 100,
Oh, that's okay.
1,000.
And the diameter is 100 nanometers. That's okay.
Some of the most peculiar effects occur when things are small, as you can imagine. Right. Okay, so this is the connection I wanted to make with some of the work that Nigel has been talking about. So for these types of structures, remember that in my case, the cell is not closed. I have a pneumatic isotropic interface somewhere at a macroscopic distance, which on this scale is somewhere in infinity. And so here what I have is homeotropic anchoring at the surfaces, and I vary the opening angle, and you find these different structures only at pi over 4. These two structures coexist, so it's degenerate because we have K1 equals K3. And so we display the same, and so we have these structures, and you can see the colored bits are defects. You cannot avoid defects in this case. And the brown, and that's sort of interesting too, the brown is the value of the surface order parameter, which is slightly higher than the bulk. This is at wetting. And
So you don't allow your director to go perpendicular?
I don't have 3D,
Okay.
but yeah, I can tell you why. Well, it's technical. It's just basically. So this is probably not sexy, but important. So here we actually try to figure out how much of this elastic free energy comes from the surface, so from the singularities in the surface, and how much does not. And so what we have here is some analytics. You can actually calculate the contribution from the surface singularities. And José Manuel Romero Henrique did this, and this is all published. And then we can do the Landau-de Gennes. We can subtract this analytic contribution, and it should not depend on the size of the grooves.
Please forgive me, I'm just trying to understand. The surface anchoring is homeotropic.
Yes.
So why do you say it's hybrid? Because the air
Oh,
would be homeotropic as well.
No, in this model I put no.
So you don't have air. It's not.
No,
free. You have a planar surface.
I have a pneumatic isotropic, so it's planar.
Okay.
But I can have other.
No.
I can have other. That's not the most relevant. Anyway, this is the elastic contribution. The elastic contribution really comes mostly from the defects in this geometry, and the way we can check that is by doing the full numerics, subtracting what comes from the defects analytically, and check that this difference does not scale with the size of the grooves. And I think this is the full phase diagram. And so here, just L over Xc goes from 32 to 96.
But since your defects are located at the interface, instead of the molecular scale Xi, you should have the surface anchoring length, which is much larger, and it's much softer core when it's at the surface, because it's only anchoring that it is fighting against.
Let me see if
So it will kind of make life easier for destinations when they are at the surface.
Mm-hmm. But here I don't impose anything.
But you put L over Xi. Yes.
So what I'm saying, it's a little bit irrelevant. What I'm saying is that this difference does not depend on the size of the. I think I understand what you're saying. And if I put another value there, I'll change the function b, but I won't put any dependence on big L. Big L is the size of the pattern. What I'm trying to say is that there is no dependence in this difference on the size of the pattern itself.
Okay.
Okay, but the approach is very, very slow to thermodynamics. I mean, that's basically what I want to say. This is the anchoring transition, the strength, this is the opening angle, and in dash dot below here, you have what you would expect just from the thermodynamics, but this free energy, really, there is this log. I mean, eventually you get the thermodynamic limit, but the thermodynamic result, but because of this log, the approach is much, much slower than you would expect, and you cannot avoid it with the geometry that you chose. Okay, this is now, I have to go quickly, it's going to go only through the overview. Now if you have these sinusoidal surfaces, you don't have these surface singularities, okay? So you calculate all the different states, and you have dry state, a wet state, a field state. You have more, these are the stable ones. You have more, these are also pneumatic wet states, but there are defects. The defects are the yellow things with the red dots. And then you write the phase diagram, you just compute the free energies, and you have, again, anchoring strength versus, that's just the amplitude times the wave vector of your sinusoid. And what you find here is that below, so for very weak surface anchoring, you have no alignment. So this is isotropic, okay? And then this is the planar limit. This is the planar limit. And as you go here, it gets more and more rough. So it gets more and more schizophrenic.
What are the units of your anchoring?
My units of the anchoring, Oleg asked me that. It's in...
No?
No, it was 3 months ago.
But,
So I thought that
okay.
even more.
No. I tried to show it in the transparency a while ago. But that W at the planar interface sweating is the same value as the pneumatic isotropic
Gamma.
surface tension, gamma.
But still, okay. Well, just what these are Newton per meter.
No, these are not, these are my reduced units, where my Q is 1, my tau temperature is 1. So this is 0.17 in my funny units, which would give you whatever it is if I put in the data. I'll show you.
No.
I did check. But so what I was going to say here is that basically on the left you have the planar, on the right you have the non-planar, the rough case, and one here you have wetting, as you would expect. You recover the planar limit. Here you get field states, and you don't actually get wet states. And the reason why you don't get wet states, by increasing the, in a normal fluid you would get the filling or the field state, and then by increasing a little bit the anchoring, you would get the wet state. Here you don't, because basically on this side of the graph, the wet states have defects. So they're really much more energetic. They cost a lot of free energy, and so you don't have these defects. And I'm really going to finish. I won't show you the details of the last case, but in the last case, I'll just give you the overview. So the last case, for very planar surfaces, we have the same as for the sinusoids. For very rough ones, we have the same as the sinusoids. In the middle, however, we have all sorts of field states. We have different surface states with different textures, with different free energies, and the phase diagram can become a lot more complicated. This is a bit about the numerics. We use finite elements with adaptive meshes, and this is a typical grid, typical accuracies. The accuracy, you go up as much as you want. If you fly from the phase boundaries, you don't need to go to these. And I think I'll go to the end, because I think those are the most important messages, and I just want to show you, oops, this is not my computer. I want to show you some open questions here. Oops, no, this is the thanks, it's before should be. Okay, quite apart from some of the things I've said and some of the things that I've heard here, there are some sort of general questions, and they may be relevant. One of the things is, what is the role of the anisotropy of the elastic constants? And again, what is the general but consistent surface potential that you should use? And things depend on that symmetry as well. And these are general questions, not just related. The first one is totally general. The second one is related to surface problems. And the third one is what Oleg asked, what about the third dimension? Of course, if you have a third dimension, then you can have things twisting and so on, like in that experiment that I showed you. It's just that at the moment, it costs a lot more to put I mean, the numerics become much more demanding. It can be done, but it cannot be done over the whole range of parameters as we've done here. One other thing which is important, and goes back to what I said at the beginning, is that if you want to look at constant volume problems, droplet-like, so you have to put back the density and the surface tension. Here you can play with the L's, but you really only have the Q order parameter. So if you really want to use, you really need to get the surface contribution, the interfacial tension, the contribution from the density to the interfacial tension. Last but not least, and as I said, even today I was reading a paper on that, the phase diagrams I showed you, and I didn't show you the last one in detail, all these transitions are first order, basically because although the differences in free energy are small, there is a lot of, the bulk transition is already weakly first order, but the difference in symmetry makes these things first order. There was some interest in getting to look at some of these things in the continuum case because, as I said, there is some connection with planar, the famous planar critical wetting, where fluctuations are really important. I mean, in these systems, nobody has any idea what the fluctuations do, even at the first order transitions. But in the critical case, people have looked at these, they know what they do, but they haven't found a system where to measure them. So finding a system would be, and of course experiments. I mean, I think there is still a challenge to explain some of the available experimental results. And I think some of the limitations are numerical, but others are really from the theory. I really think this is where I would like to finish, but not without thanking the people who really worked on this. It's co-worker Pedro Patricio really started this. Nuno, my postdoc, he was a student of both of us. Matthew Blow is a postdoc in Lisbon now. He was a student of Julia. Zara is a student in Iran. And José Manuel Romero Henrique, whose name is a bit too long to write there, from Sevilla. It's not really in Lisbon, but it's, to me, it's as if he were. I wish he was in Lisbon. And thank you all for your attention.
Thank you very much, Margarida, for your talk, and I'd like to invite questions.
I'm a bit unhappy with your estimation of anchoring energy as a surface tension. Anchoring energy is an isotropic part of surface tension. It should be at least 10 times smaller. Alec corrects me if I'm wrong. In fact, it's even less.
It's at least 10 times thermotropic.
10 times stronger than the...
No, bigger than isotropic contribution to the surface tension. So your W is smaller than 1. That's kind of okay.
It is much smaller than 1, yeah. But also here I'm only looking...
It's 10 times smaller, I would say.
No, but here, okay. So this is not the anchoring, just anchoring, because I do have an interface. It's only within Landau theory that this doesn't have a difference in energy. The real interface will have a difference in density. And so it will have the real surface tension. I agree with you. The real surface tension is not the anchoring energy.
Yeah, it's much higher.
Yeah, but what comes in here, if you want to balance the free energy of the surfaces, you have to pay for the free energy you create. So you may not call it that. So that may not be the anchoring energy in the usual sense. That is the full, what you have to, I mean, I said some terms will...
You commented on the planar degenerate and the homotropic surface. Can you say something on the case of planar homogeneous?
Planar homogeneous, yeah.
Mm-hmm.
So if it is planar in the surface and homeotropic here,
or even just planar surface.
which one do you want?
No, they are separate. I mean, I would like both, but I mean, I was really concerned.
Okay, if you have this planar, homogeneous, nobody worked out the family. There's no longer a full mapping with the scalar order parameter because now the surface and the interface will be biaxial. The biaxiality will only be around that region, and the general features will be the same as the homeotropic general features.
planar orientation, you have a preferred direction in the plane.
No, as I say, details the difference. So if you look locally, both the surface and the interface in the case of homogeneous planar will be biaxial. So there is, but this biaxiality is over the interface and surface alone. So the general, but the nematic is like
this
uniform.
This is not really the one I meant, because I was concerned by a wetting over, say, a face of the crystal, where you have planar and homogeneous. You have preferred direction in the plane of the crystal. And then you have a droplet, so you can have air, which would probably be homotropic or whatever at the other end. So my question is, if you can comment of the difference between the same droplet landing on a face of a crystal and landing on a plane of the on glass, say.
On glass.
Or on glass.
Okay, when it lands on glass, the solid, so now we have the isotropic. You want the isotropic drop and see how the nematic.
If I can choose nematic, but
Nematic.
please, it's to you.
No, because if you have nematic, you cannot have
Well,
the transition that I was
It's a
talking about.
normal lipid, so I don't bother.
Okay, if you have the nematic and if there is a direction
Right.
in the
That's
plane,
the one, yes.
so close to the plane, the nematic, if it's strong enough, will adopt that direction. Okay, and then at the free surface, because there's a nematic and another
Yes.
isotropic phase outside. At the free surface, if the droplet is macroscopic, millimeters, macroscopic, the free surface will have the preferred direction of the free surface. And in between, there will be some distortions, but over a macroscopic scale.
Yeah, no, that is okay. We have simulated that. But I think basically I was wondering if, from the point of view of Wenzel versus Baxter type of anchor, there is a difference that you think. If my surface, corrugated surface, or my surface is a glass degenerate, or if it is a crystal. I mean, just a feeling that.
I don't know.
But I can
I don't
probably
know.
help, because
Uh-huh.
in these simulations, everything is two-dimensional. That corresponds to fixed in-plane anchoring, that corresponds to the anisotropic substrate. It's not a glass, because the director is not allowed to escape the plane of simulations and to look perpendicular
But
to
it's
the-
always on the topic here, so.
Yeah,
the glass
homotropic at the
the
top,
glass
but
would give plane.
planar unidirectional at the other surface. It's always unidirectional at the
Yes.
planar surface.
Yes, but I was trying to
That's it.
trying to guess the answer in more general
So
terms.
that corresponds
Yes.
to the strongly
corresponds-
anisotropic crystalline substrate. That is not
one crystalline.
right. Yeah, which is in the plane of your.
Yes, no, you're completely right. I was trying to say that in general, and I think this is, if you just have, well, I mean, if you have random like glass, you can have this nematization surface transition that Tim looked at and then has been seen apparently in the free surface. So even in the isotropic phase, the molecules can be randomly planar but randomly ordered, and even above the nematic isotropic transition, they can align. They can choose a preferred
I
direction.
think it's time for Tim to have a say.
Yeah.
Actually, I was, first of all, let me make a comment. And that is, you took some experimental results. I don't know where you took the experimental results, because some of my experimental results, the ones that are quoted by me, came from a paper that was in Russian, I think in Russian sentiment,
This
or
is
possibly in Ukrainian sentiment.
molecular crystals, liquid crystals, 2008.
Ukrainian.
Okay, of course it was Ukrainian. Okay, all right. So the point, all right. So
If it was
taking a
correct,
discontinuity in the 2008 paper, it's a little bit dangerous, because actually what we were trying to do was look at liquid crystal capillarity, right? And what we were particularly interested in was the fact that different methods of measuring, methods of measuring surface tensions, which are known to give the same answers if you're doing it for a nice ordinary isotropic fluid.
But I divided the gap by 100.
Yeah, but sometimes
No,
sometimes
I
you
couldn't do
get
the
gaps that are going in the
gap.
wrong direction
Yeah.
in the kind of experiments that
But
that we
if
do,
it is
as I recall.
equilibrium, the gap cannot be bigger than sigma and I.
No, the point being that the experiments, because the experiments aren't quite measuring what you think they are, although we don't
Yeah,
know
I had
exactly
this
what they
discussion with
are,
Dominic
the
last
gaps are going in the wrong, you you can't just naively
I've seen
apply
gaps
them.
10 times bigger, but I have.
I mean, I don't know what the answers are, but those are interesting questions in and of themselves, which are, what do classical surface tension experiments do when they measure surface tensions of liquid crystals? Because each of the different methods will be measuring something else, and the something else will also always include a certain amount of elasticity and various things like that. So I think that's just a sort of caution in terms of interpreting experimental results. It doesn't have any direct problem. Okay, so my next question is, when we write down the Landau theory, we don't really know what's happening at the surface, right? We don't really take it terribly. I mean, of course it's true that I sort of made a guess that said, well, let's compare the Landau theory to some kind of mean field theory and specifically forget about what's happening on the other side of the wall. But I don't really believe that my surface is flat. I really think that these are just phenomenological parameters.
Mm-hmm.
And I really think that those phenomenological parameters have something to do with the microscopic parameters and something to do with the roughness of the surface. And what I would like is to know whether or not I can go from this, right, you've taken this sort of groovy type surface, and what I'd really like to say is, gosh, I don't care about the details of your groovy type surface. I just want to parameterize it. Or alternatively, I want to know whether I can't parameterize it, because it might be, for instance, that with your pictures you're seeing some filling transitions or something that couldn't possibly happen.
It depends on scale.
That's right. It depends on the scales. No, that's quite clear. Yeah.
Sorry.
Yeah.
All right. Sorry. In what sense? I mean,
if characteristic scales on the surface is much larger than the coherence length, correlation length, in this case it doesn't matter. If it's
but
compatible.
coherence length. Do you mean the microscopic coherence length that crops up in the Landau theory, or the macroscopic?
No, Landau theory, in the sense of Landau theory. It's
all right, but
40 nanometers.
Right,
of the
but you
transition,
see,
a little
all
bit
right,
more.
but let me go a little bit further than that. If I then, I mean, most of my action at one of these rough surfaces isn't going to take place within, 1/10 of a degree of the rough. Most of my action is concerned with trying to figure out how, what is the effective anchoring, right? And I want my effective anchoring, right? And those length scales are certainly going to be much larger than, right? And those length scales can, right, and those anchoring transitions to some extent can be sort of interpreted in terms of some sort of quasi-Landau theory at the surface. So my question is, to what extent can the kind of things that Margarida is doing make contact with, if you like, a more macroscopic
Might
theory?
be not, because you are discussing quasi two-dimensional case. In this case, transition could be not Landau-like, but Berezhinsky-Kosterlitz-Taulis-like. It's totally different story.
I'm afraid I need.
Okay.
Yes. Okay.
Why don't you answer the
No,
question?
I don't want to answer. I think there are different length scales the way I see it, and I think in this particular case it might not be. I mean, for example, the experiment that they did with the FD virus, I mean, they really have the grooves, and so the grooves cannot be smooth or integrated out. So it really depends on the length scale of the grooves. If you talk about molecular grooves, then of course you're right, and I think you get some effective anchoring. And I also admit that what I call anchoring is really got a surface tension contribution, at least nematics as a topic, which within Landau I cannot really do much better. Within the macroscopic series you can separate them because you have the density. So anyway, but some of the open questions that I have there, I've seen in other talks, and I think some of them I would like to understand a bit better. Okay, so
Let us thank again our speaker.